Welcome to this coding problem walkthrough. Today, we'll be exploring problem number 56, merge intervals. In this problem, we'll tackle the challenge of merging overlapping intervals efficiently. Let's dive in and break it down step by step. The problem is about merging overlapping intervals. Imagine you are given a list of intervals, where each interval is defined by two numbers, a start and an end. Your goal is to combine any intervals that overlap into a single interval, ensuring that the output contains only non-overlapping intervals that fully cover the same range as the input. For example, if you have two intervals that share some common portion, they should be merged into one. The input is a list of such intervals, where each interval is represented as a pair of integers, and the output should be another list of intervals after merging any overlaps. Looking at the first example, the input intervals are 1, 3, 2, 6, 8, 10, 15, 18. Here, the intervals 1, 3, and 2, 6 overlap because their ranges intersect. These are combined into 1, 6. The other intervals, 8, 10, and 15, 18, do not overlap with any others, so they remain as they are. The final result is 1, 6, 8, 10, 15, 18. In the second example, the input is 1, 4, 4, 5. While these intervals only touch at the boundary, they are still considered overlapping, so they are merged into a single interval, 1, 5. In the third example, the input list is 1, 4, 2, 3. Here, 2, 3 is completely contained within the range of 1, 4. Since there is no need to keep the smaller intervals separately, the result is just 1, 4. Now, moving on to the constraints, the problem allows for up to 10,000 intervals in the input list. Each interval consists of exactly two numbers, where the start value is always less than or equal to the end value. These constraints ensure that the input is well formed, and the algorithm must handle large inputs efficiently. There are a few important edge cases to consider. If the input contains only a single interval, like A, B, then no merging is required, and the output should simply be the same interval. When all intervals are non-overlapping, such as 1, 2, 3, 4, 5, 6, the output should also remain unchanged. Another scenario involves intervals that touch at their boundaries, like 1, 4, 4, 5, 5, 6. These should be merged correctly to eliminate any boundary overlaps. Finally, if all the intervals overlap into one large interval, for instance, 1, 10, 2, 6, 3, 5, the output should reduce to a single interval that spans the entire range. Addressing these cases ensures the solution is comprehensive and robust. When tackling the merge intervals problem, one approach we can consider is the brute force method. The idea here is to compare every pair of intervals to check if they overlap. If two intervals do overlap, we merge them into one and update our list of intervals. This process is repeated until no further merges are possible. To determine if two intervals overlap, we check whether the start of one interval lies within the range of another interval. However, this method comes with significant drawbacks. Since we're performing repeated pairwise comparisons and making adjustments each time, the time complexity becomes n squared, which is prohibitively slow for large input sizes. Additionally, it doesn't take advantage of any inherent structure in the data, which makes it inefficient. While the space complexity is manageable at n for the output list, this approach simply doesn't scale well, and that's why it's not suitable for this problem. Instead, we shift our focus to a more optimized approach that leverages sorting. The optimized approach, often referred to as the sort and merge strategy, provides a much cleaner and more efficient way to solve this problem. The key idea is to sort all the intervals by their start times, which ensures that any overlapping intervals are adjacent. This eliminates the need for multiple comparisons across the entire list. Once sorted, we can traverse the list and compare each interval to the last merged interval. If they overlap, we merge them into one. If not, we simply add the current interval to our result list. This approach has significant advantages. Sorting the intervals takes n log n, and the subsequent merging step is performed in n, leading to an overall time complexity of n log n. The space complexity remains O, n, for the output list. This balance of efficiency and simplicity makes it the most practical solution. Other approaches tend to be less efficient or overly complex, which we'll explore next. Among the various strategies considered, the sort and merge approach stands out as the best choice due to its efficiency, clarity, and ease of implementation. Sorting the intervals ensures that any potential overlaps are adjacent, which reduces redundant comparisons and makes the merging process straightforward. This scalability allows it to handle large input sizes efficiently. The simplicity of the algorithm also means that it can be easily understood and implemented without the need for complex data structures or additional overhead. With an optimal time complexity of O, n log n, it achieves the best possible performance for this problem, given that sorting is a necessary step. Alternative strategies, such as divide and conquer or tree-based methods, introduce unnecessary complexities without providing any significant advantage in terms of efficiency. By leveraging the sorted order and minimizing redundant operations, the sort and merge approach offers an elegant and high-performance solution to the merge intervals problem. The problem we're solving here is to merge overlapping intervals from a given list. Each interval is represented as a pair, start, end, where the start value is less than or equal to the end value. These intervals may not be sorted initially. To solve this, the first step is to sort the intervals based on their start times. Sorting ensures that overlapping intervals are adjacent in the list, making it easier to process them sequentially. The sorting step can be implemented using your language's built-in sorting function, and it runs in O, n log n, time. After sorting, we initialize an empty list called merge to store the resulting intervals. This list will be built dynamically as we iterate through the sorted intervals. The iteration involves looping through each interval, checking whether it overlaps with the last interval and merged, and taking the appropriate action. Let's begin with the details of how we handle these cases during the iteration process. When iterating through the sorted intervals, there are two key cases to consider. In the first case, if the start of the current interval is less than or equal to the end of the last interval in the merged list, it means the intervals overlap. To merge them, we update the end of the last merged interval by taking the maximum of the two end values. This step ensures that the intervals are combined into one, encompassing the entire range. In the second case, if the start of the current interval is greater than the end of the last merged interval, it means there's no overlap. In this situation, we simply append the current interval to the merged list, as it starts a new group of non-overlapping intervals. After processing all the intervals, the merged list will contain the final set of merged intervals, which we then return. Sorting the intervals up front is crucial, as it guarantees that we only need to compare each interval with the last one in merged, which minimizes unnecessary comparisons. This algorithm is designed to handle various scenarios effectively. For fully overlapping intervals, it correctly merges all of them into a single interval. For non-overlapping intervals, each one remains separate in the resulting list. To achieve this, we use a few key data structures. The input list stores the original intervals, the merged list dynamically stores the merged results, and sorting is performed using an efficient built-in algorithm like timsort, which operates in O, n log n, time. Analyzing the overall complexity, we see that sorting the intervals takes O, n log n, and iterating through the intervals takes O, n. This gives the algorithm a total time complexity of O, n log n. The space complexity depends on the sorting algorithm. In Python, timsort operates in place, so it requires O, 1, additional space. The merged list uses O, k, space, where k is the number of merged intervals. Thus, the overall space complexity is O, k. Let's look at the pseudocode to see how this logic is implemented step by step. The pseudocode for merging intervals starts by handling the edge case where the input list is empty. If there are no intervals, we return an empty list immediately. Next, we sort the intervals by their start times to ensure they are processed in the correct order. After sorting, we initialize an empty list called merge to store the resulting intervals. We then loop through each interval in the sorted list. If the merged list is empty or the current interval does not overlap with the last interval in merged, we append it directly to merged. Otherwise, if there is an overlap, we update the end value of the last interval and merge to be the maximum of its current end and the end of the overlapping interval. After completing the loop, we return the merged list, which now contains all intervals merged correctly. Let's walk through an example to see this algorithm in action. Consider the input intervals 1, 3, 2, 6, 8, 10, 15, 18. First, we sort the intervals, which in this case are already sorted as 1, 3, 2, 6, 8, 10, 15, 18. We then initialize an empty list merged. Processing begins with the first interval, 1, 3, which is added to merged, resulting in 1, 3. Next, we process 2, 6. Since it overlaps with the last interval and merged, we merge them by updating the end value to 6, resulting in 1, 6. Moving to 8, 10, there is no overlap, so it's added directly, giving 1, 6, 8, 10. Finally, 15, 18 is processed and added to merged, resulting in 1, 6, 8, 10, 15, 18. The final output is 1, 6, 8, 10, 15, 18, which represents the merged intervals. The provided Python solution efficiently solves the merge intervals problem. Here's the step-by-step explanation. 1. Sorting the intervals. We begin by sorting the list of intervals based on their start times. Sorting ensures that we process the intervals in sequential order, which makes it easier to identify and merge overlapping intervals. The sorting operation has a time complexity of O, n asterisk log, n, where n is the number of intervals. 2. Initialization. We initialize an empty list called merged. This list will store the merged intervals as we process the input. 3. Iterating through intervals. We iterate through each interval in the sorted list. If the merged list is empty or the current interval does not overlap with the last interval and merged, determined by checking if the end of the last interval is less than the start of the current interval, we append the current interval to merged. If there is an overlap, i.e., the end of the last interval is greater than or equal to the start of the current interval, we merge the two intervals. This is done by updating the end time of the last interval and merge to the maximum of its current end time and the end time of the current interval. 4. Returning the result. After processing all intervals, the merged list contains the merged intervals, which we return as the result. This approach is efficient because we only sort the intervals once, and then we process each interval in a single pass. The overall time complexity is O, n asterisk log, n, dominated by the sorting step, and the space complexity is O, n, for the result list. This is the Java implementation of the merge intervals problem, following the same logic as the provided Python solution. The intervals are sorted by their start times, and overlapping intervals are merged by comparing their end times. Key differences include the use of Java's arrays.sort for sorting and ArrayList for dynamic storage of merged intervals. The final result is converted back to a 2D array before returning to match the expected output format. To solve LeetCode problem number 56, merge intervals, we need to work with an array of intervals, where each interval is represented as a pair of values, a start and an end. Our task is to merge any overlapping intervals and return a new array that contains only non-overlapping intervals. The solution involves a systematic process of sorting the intervals, checking for overlaps, and merging them if necessary, all while ensuring optimal efficiency. We'll go through this step by step, using examples to clarify how we manage the intervals and track changes at each stage. In the first example, the input is a set of 4 intervals, 1, 3, 2, 6, 8, 10, 15, 18. The first step is to sort these intervals by their start times. Here, the intervals are already sorted, so we can proceed to initialize an empty list called merge to store the results. Next, we process each interval one by one. Starting with 1, 3, since merged is empty, we add it directly. 4, 2, 6, we check if it overlaps with the last interval and merged, which is 1, 3. Because 3 is greater than or equal to 2, they overlap, so we merge them by updating the end of 1, 3 to the maximum value, which is 6. This gives us 1, 6, and merged. 4, 8, 10, there's no overlap with 1, 6, so we add it directly. Similarly, 15, 18 doesn't overlap with 8, 10, so it's added as well. The final result is 1, 6, 8, 10, 15, 18. In the second example, we have two intervals, 1, 4, 2, 3. The first step is sorting, but these intervals are already sorted. We again initialize an empty merged list and start processing. For the first interval, 1, 4, since merged is empty, we add it directly. Next, we look at 2, 3. To check for overlap, we compare its start, 2, with the end of the last interval and merged, which is 4. Since 4 is greater than or equal to 2, these intervals overlap. To merge them, we update the end of 1, 4 to the maximum of 4 and 3, which remains 4. Hence, the merged result stays as 1, 4. This example highlights how the solution handles cases of complete overlap, where one interval is fully contained within another. In the third example, we have three intervals, 1, 2, 3, 4, 5, 6. After sorting, the intervals remain in the same order. We initialize merged as an empty list and process each interval. For 1, 2, since merged is empty, we add it directly. Moving to 3, 4, we check if it overlaps with 1, 2. Since 2 is less than 3, there's no overlap, so 3, 4 is added to merged. Similarly, 5, 6 does not overlap with 3, 4, so it is also added. The final result is 1, 2, 3, 4, 5, 6. This demonstrates how the solution handles cases where no intervals overlap, simply appending each interval to the result list. The key to this solution lies in a few fundamental insights. First, sorting the intervals by their start times ensures that we process them in the correct order, making it easier to identify overlaps. Second, the overlap check involves comparing the end of the last interval and merged with the start of the current interval. If they overlap, we merge by updating the end to the maximum of the two intervals. If there's no overlap, we simply append the current interval to merged. The time complexity of this solution is dominated by the sorting step, which takes O, n log n. The single pass through the intervals is O, n, making the overall complexity O, n log n. This approach is both efficient and clear, handling edge cases like complete overlap, partial overlap, and no overlap seamlessly. With this, we achieve an optimal and robust solution for the problem. To analyze the time complexity of our solution, we break it into two main components, sorting the intervals and merging them. First, the sort function is used to arrange the intervals based on their start times. Sorting an array of n elements typically takes O, n asterisk log, n, time, where n is the number of intervals. Next, we have the merging process. In this step, we iterate through all n intervals exactly once. For each interval, we either append it to the merged list or update the end time of the last merged interval, and both of these operations take constant time, O(1). Thus, the merging step has a linear time complexity of O(n). When we combine the sorting and merging steps, the overall time complexity becomes O, n asterisk log, n, plus O, n, which simplifies to O, n asterisk log, n, since the sorting step dominates. Now, let's evaluate the space complexity of the solution. The sort function, often implemented using a comparison-based sorting algorithm like timsort, requires O, log, n, extra space for its recursion stack. Additionally, the merged list is used to store the result. In the worst-case scenario, where no intervals overlap, all n intervals will be added to the merged list, requiring O, n, space. Since no other data structures are used in the algorithm, the total space complexity is the sum of these two components, O, n, for the merged list and O, log, n, for sorting. This gives us an overall space complexity of O, n, as the linear term dominates for large N. Now we can look at the best, average, and worst-case scenarios for this algorithm. In the best case, all intervals are already sorted and non-overlapping. The sorting step still takes O, n asterisk log, n, but the merging step is straightforward and only involves appending intervals to the merged list. This means the overall time complexity remains O, n asterisk log, n. In the average case, which reflects most real-world scenarios, some intervals will overlap, and the algorithm will need to merge them. However, the sorting step still dominates, so the time complexity is still O, n asterisk log, n. In the worst case, all intervals overlap completely, such as an input like 1, 10, 2, 9, 3, 8. Here, the merging process involves updating the end time of the last interval during each iteration. Even so, the sorting step remains the dominant factor, and the overall time complexity is O, n asterisk log, n. Finally, let's compare this optimized approach to a brute force method. A naive approach would involve examining every pair of intervals for overlaps and merging them iteratively. This would require O, n squared, comparisons in the worst case, such as when all intervals overlap. This quadratic time complexity makes the brute force method highly inefficient for large input sizes. In contrast, the optimized approach first sorts the intervals, allowing the merging process to be completed with a single linear scan. By reducing the problem to sorting, we achieve a much more efficient time complexity of O, n asterisk log, n. The space complexity is also minimal, as the only additional structure used is the merged list, which grows linearly with the number of intervals, making the space complexity O, n. This demonstrates the clear advantage of using the optimized approach over the brute force method, particularly for larger datasets. When working with the merge intervals problem, there are several common mistakes to watch out for. First, not sorting the intervals by their start points before attempting to merge them is a frequent error. Without sorting, you can't guarantee that intervals are in the correct order to determine overlaps accurately, which can lead to incorrect results. Another common issue is misunderstanding the overlap condition. Remember, two intervals overlap when the end of one interval is greater than or equal to the start of the next. Misinterpreting this condition can cause you to miss overlaps or merge intervals incorrectly. A further pitfall is modifying the list of intervals while iterating through it. Doing so can lead to skipped intervals or index errors. Instead, always create a new list to store the merged intervals. Lastly, overcomplicating the logic is another trap. Nested loops or multiple conditions for overlap checks often make the solution unnecessarily complex. A simple, linear scan after sorting is usually sufficient to solve the problem efficiently. Now, let's consider another frequent mistake, ignoring edge cases. It's important to handle scenarios like an empty input, a single interval, or a set of intervals that don't overlap at all. Overlooking these cases can lead to runtime errors or incorrect results. From an interview perspective, there are several key insights to keep in mind. First, sorting the intervals simplifies the problem dramatically. Once the intervals are sorted, you only need to compare adjacent intervals to check for overlaps, which reduces the complexity to O, n log n. Additionally, this problem often appears in variations, such as finding gaps between intervals or handling intervals with weights. It's a great opportunity to showcase your understanding of patterns like merge intervals. During an interview, focus on clearly explaining your sorting step and how you plan to merge intervals iteratively. Avoid diving into implementation details too early. Finally, while brute force solutions with O, n squared, complexity might work for small datasets, they're inefficient for larger inputs. The optimized approach of sorting followed by a linear scan strikes a good balance between simplicity and performance. This problem is closely related to several other interval-based challenges that are worth exploring. The core problem is, of course, LeetCode 56, merge intervals. Beyond that, LeetCode 57, insert interval, asks you to insert a new interval into a sorted list of intervals. LeetCode 435, non-overlapping intervals, focuses on removing the minimum number of intervals to make the rest non-overlapping. Another interesting variation is LeetCode 986, interval list intersections, which involves finding intersection points between two lists of intervals. In terms of alternative approaches, the brute force method involves comparing every pair of intervals for overlaps. While this approach is simple to implement, its O(n)² complexity makes it impractical for larger datasets. The sweep line algorithm is another option, where you handle the start and end points of intervals separately. This method has a complexity of O(n log n, similar to the sorting-based approach, and is particularly useful for advanced scenarios, such as dealing with intervals that have additional attributes like weights. However, it's often unnecessary for basic merge problems. Another advanced approach involves using data structures like treemap in Java or sorted dict in Python. These structures allow you to maintain sorted intervals dynamically. The complexity remains O(n log n, similar to the sorting-based method, but the trade-off is added implementation complexity. These dynamic data structures are particularly valuable in scenarios where intervals are updated frequently, such as when intervals are inserted or removed in real time. While they may not be the best choice for the core merge intervals problem, they're worth understanding for more dynamic or complex variations of interval-related challenges. Great job working through this problem. We covered how to merge overlapping intervals efficiently, focusing on sorting and iteration. Remember, this is a classic example of a greedy algorithm, and it's perfect for interview prep. Thanks for tuning in. Don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!